All right. Can y'all hear me pretty well on your end?
Yeah, we can hear you.
Perfect. How about everyone else?
Yeah, I can hear you.
All righty, good. Works with me. All righty. Welcome to day 2 review, where we just talk about integration techniques. All the fun that we had way back in the day. All right. So, for people who weren't here yesterday, if you have like a private message you want to send it to Q&A, not to Scott Scruggs, because I'm running on my tablet. But since my tablet's recording the Let's Share, if you send a private message, I like to keep it private. So you send it to Q&A, I'll be able to see your message on my laptop. All right. So let's get back to the good old days where we talked about integration techniques. And the first integration technique we've ever talked about was the one that we had back in test 1. Which was integration by parts. And keep in mind that to know when to use integration by parts, in general, is going to be integrals of this form. And the idea of what this formula is saying is when to use integration by parts. Is if you have a product of two functions and one is easy to take the derivative of and the other function is easy to take the antiderivative of. So when to use integration by parts? When you have a product of two functions in the integral and the second part, when you do it, I always think of one function is easy to integrate or easy to take the antiderivative of. And one is easy to take derivative. And the way that our integration by parts formula works is I'm going to define two brand new variables, u to be the function that is easy to differentiate, and the second function with the d of x, I'm going to define it to be dv. So I have u equal to f of x and dv equal to the derivative of g of x, d of x, or that. Next thing that I do is I take the derivative of the function that I paired with u, because that is easy to take the derivative of. And I call phi to be the antiderivative of what I've gathered. And what integration by parts formula tells us is the integral of that product above, which I'll now replace with u times dv, is equal to the product of these two married together outside of the integral, the product of these two married inside of an integral, which will change into v du, and they're joined together by subtraction. And that's going to be our general formula for integration by parts. Now, if we had a definite integral, our formula is still the same. It's just now we're going to have some balance we have to deal with. So the modification that we're going to do is the following. Keep the balance with that integral. Now for the u times v, you could assume that I already evaluated that outside of the integral. And because I'm taking a definite integral, I'm going to have to remind myself that, just like with fundamental theorem of calculus, I'm going to have to define that as that at the upper limit, and then subtract it off by the u times v at the lower limit. And that's going to be our integration by parts in a nutshell. And if you always want to think of which takes priority of what I want to choose for u, want to choose for dv, that's where that acronym ILATE will come into play. I stands for inverse trig function. L stands for logarithms. So I'll write that down. Inverse trig, logs. A stands for algebraic. And what I mean when I say algebraic, any polynomial is fair game. The reason why I say algebraic and not polynomials is so I can capture functions like that. Square root of x squared minus 1. T stands for trig. E stands for exponential. And the way that I'm going to read that acronym is, if I read from top to bottom, that's going to be my hierarchy for what I want to choose from dv. Because going from top to bottom, they're harder to take the antiderivative of. So that means if I see an exponential, I'm automatically choosing that for my dv in an integration by parts problem. Because the antiderivative of e to the x is just e to the x. And this will be trig, vice versa. There's some audio going on. Someone else is in, so thank you. All right, and I read that way. And for my choice of u, if I read from bottom up, that starts from my hierarchy for what I want to choose for u. Which means if I see inverse trig function like inverse sine, that's automatically my choice for u, because I could quickly take its derivative in comparison to taking its antiderivative. So there's integration by parts in a nutshell. Time for our first warm-up problem to get us started. So the first problem for today is evaluate the following integral. So try to integrate the integral of s squared times e to the negative 4x. I'll give y'all a few minutes to work on it, like about between 7 or 8 minutes or so. If y'all have questions, unmute your mic to let me know, or post it on the chat to let me know. All right, try your best on this problem and start working. Whoever that is, please mute your mic because I'd rather not hear that audio. Alrighty, y'all. Give me a status report. How's this problem going? There is a possibility that you might have to use integration by parts again. Unique. So the answer is yes. All right. give y'all about another 3 minutes to work on it, 3 to 4 minutes to work on it. And like I said, if y'all have questions, please let me know. Alrighty, let's go ahead and go over the solution. So y'all probably caught that was going a pretty long one. So first we're going to do integration by parts. Based on what I have for the integral, what would be my choice for u and what would be my choice for dv based off the integral that I have? Bingo. Thank you, Jason. U would be at squared because according to Eilate, an exponential has the highest hierarchy for my choice for dv. And my choice for dv would be e to the negative 4x. Overall, you're right, Jason. Just remember that we have to include dx when we're defining dv because it's a differential. All right, so that means I'm going to take the derivative of what I called u, and then I'm going to integrate and take the antiderivative of what I have for v. E to the negative 4x, but because I have a constant of a negative 4, I must divide by negative 4 to counteract that. And integration by part says, these two are going to get married outside of the integral. These two are going to get married inside of the integral. And I'm going to join them together by subtraction. So that means our integral of x squared times e to the negative 4x dx equals x squared times, and I'll go ahead and put the negative sign up front, e to the negative 4x over 4 minus the integral of 2 times x times e to the negative 4x over negative 4 dx. Let's try to simplify inside this integral real quick. I have 2 multiplied by 1/4. So that reduces to a 2 in my denominator. I also have a negative sign inside the integral. So when I use my property of integrals that says a linear constant comes out, that's going to change from a negative sign to a plus sign, which means I now have minus x squared times e to the negative 4x over 4 plus, since 1/2 is a constant inside of the integral, my property of integrals get to tell me I could take that 1/2 outside, and I'm just left with taking the integral of x times e to the 4x, e to the negative 4x dx. And as Unique mentioned before, for this integral, we're going to have to do integration by parts again. So I had to use integration by parts again in order to tackle that guy. So let's do our scratch work. Choose a new u. We're going to choose a new dv. Same thought process as before. I still have an exponential function, which means that will have hierarchy for dv. Let's move you a little bit better. And u would be x. So d will just be 1 times dx. And v would be e to the negative 4x divided by negative 4. And integration by part tells me marry the u and the v outside of the integral, marry the du and v inside of the integral, join them again by subtraction, which means I now have that the integral of x squared times e to the negative 4x dx is equal to the part that I've already obtained from integration by parts, the negative x squared times e to the negative 4x over 4 plus 1/2. And I now include the brand new stuff that I obtained with my second iteration of integration by parts, which is the negative x times e to the negative 4x over 4 minus the integral of e to the negative 4x over negative 4 dx. I have a negative sign up front, so that goes out, and also the 1/4 goes out. So what I now have inside of my integral is, first copy down everything that I currently have. So negative x e to the negative 4x over 4. And taking out the constant inside of the integral, I have plus 1/4 integral e to the negative 4x dx. We're taking that integral antiderivative multiple times, so we know that its antiderivative is e to the negative 4x over 4. So I'm going to use that now to go ahead and give me that my integral equals negative x squared times e to the negative 4x over 4 plus 1/2 negative x e to the negative 4x over 4 plus 1/4 times e to the negative 4x over negative 4. Close my bracket. And because I finished taking all of the integrals, or evaluating all of the integrals through integration by parts, now I could go ahead and include plus c to denote that I'm not taking an antiderivative anymore. And if you want to, you could simplify this further by distributing that 1/2 to both parts, multiplying that to give me a negative 1/16 times e to the negative 4. So with that, after simplifying, I'm going to get negative x squared times e to the negative 4x over 4 minus 1/8 x times e to the negative 4x minus, again, because of that negative sign when I took the antiderivative of e to the negative 4x, 1/16, 1/32 of e to the negative 4x plus c. And that will be my final answer for that problem. Give y'all a minute to catch up with writing. If y'all have questions about my solution, feel free to post it in the chat or unmute your mic and just chat.
I have a quick question about the way you annotated your ILATE acronym.
Mm-hmm.
So maybe I wasn't paying attention. The arrowhead, does that go to the most preferred or the least preferred per side?
Most preferred.
So for DV, E is always for, okay, yeah, that makes sense.
Okay, yeah, I should have clarified that better. Yeah, so exponential will have the highest hierarchy for DV, and inverse trig will always have the highest hierarchy for U.
Okay, perfect, thank you.
You're welcome. Any other questions? I'll scroll back down to near the end in case y'all were writing it down. And all right. And so I do want to go over and review another integration by parts problem. And guess what I want to walk through? And it's when, for some integration by parts problems, we can loop back to the original integral. And so let's see what we do if we actually loop back to the original integral. So for the second problem, I'm going to integrate e to the x times sine of x d of x. And I'm going to let y'all know right now that we're going to loop, and during my integration by parts, I will get back to the original integral. So let's work through this together and see how we can tackle those types of problems. So I have a product of two functions, which means I'll be using integration by parts. Because I see an exponential, e to the x will have my hierarchy for dv. So sine will be my choice for u. So du equals cosine, v equals itself. And so by integration by parts, I have that the integral of e to the x times sine of x d of x equals married uv outside of the integral. Yep, that's right, Anthony. That's why I'm walking through this one, because that's going to be the main goal of this example. Outside of the integral minus integrating, marrying these two inside the integral, and then join them to together by subtraction. You need to give that pun a 2 out of 10 on my pun meter or joke meter. All right, so I have to use integration by parts again on that integral. Again, I still have an exponential, so that means I'll choose cosine for my integral, and I will choose for dv exponential since I have the highest hierarchy. So derivative of cosine will give me the negative sine of x d of x. And e to the x is boring because its antiderivative is itself. So another iteration of integration by parts will give me marry these two inside the integral, so outside the integral, so e to the x times cosine of x minus marry these two inside of the integral. So e to the x times negative sine of x d of x. I have a negative sign here as a constant in my integral. So properties of integral tells me I can factor that guy out, and I get e to the x times sine of x minus e to the x times cosine of x plus the integral of e to the x times sine of x d of x. And because of that minus up in front, I now have e to the x times sine of x minus e to the x times cosine of x minus the integral of e to the x times sine of x d of x. And so now I'm at a problem where after a few iterations of integration by parts, I will still loop back to the original problem. So let's see how we can tackle if we loop back to the original integral. And here's going to be my idea. Our end goal is to try to take the antiderivative of e to the x times sine of x d of x. And so if I ever loop back around in my integration by parts, just like back when we learned algebra way back in the day, I'm going to treat the entire integral as my unknown variable and solve for it. That's going to be my main strategy if I loop back via integration by parts. I'm going to treat this as my unknown variable, and I'm going to solve for it as if I was way back in my algebra class solving for a linear equation. And so let's do that for this problem. I want to copy down the problem again, so we have it on one line. So copy down what we currently have. All right, so now I'm going to treat this entire integral as my unknown variable, and I'm going to solve for it. First thing I need to do is to isolate on one side of the equation. I can do that very quickly by adding both sides of the equation by the integral of e to the x times sine of x d of x. On the right-hand side, those are gone. On the left-hand side, I'm adding the same variable to itself, so I get 2 times that. So after the operation, on the left-hand side, I have 2 times the integral of e to the x times sine of x d of x is equal to e to the x times sine of x minus e to the x times cosine of x. Now that I've done the operation of adding, bingo, Jason. Last thing I need to do is divide by 2 to get red. Let's change that to orange to not confuse that pink 2. Now I'm going to divide by 2 to only have the integral on the left-hand side. And so now, because I've done that, my final answer, I'll use my fancy Triforce symbol, which means therefore, the integral of e to the x of sine of x d of x equals e to the x times sine of x minus e to the x times cosine of x, all dividing by 2. And I'm now done with the integral, so I now get to include the plus c. And so that is how we are going to tackle an integration by parts problem if we do have a situation where I loop back to the original. Treat it as an unknown variable, pretend it's a linear equation, solve for the unknown. Any questions on that method before I move on to trig integrals? Take a sip of my water if you're still writing down. Hey, Unique, I just saw your comment, and yeah. All right, time for the next integration by integration technique, and that is trig integrals. And so we mainly talked about 2 MF 1080. So I'm going to mention both of them. And trig integrals are going to come out when I have sine and cosine being multiplied together. And it being raised by 2 powers. And the other trig integral that could happen is if I have tangent times secant being raised by 2 powers. And so let's figure out how we can tackle those 2 types of problems. Don't know if I can use the table. Let's see if I can fit all of it in each column. So let's start up with sine and cosine with the 3 different powers. There are 3 things that are going to occur with a trig integral of sine and cosine. 2 of them are almost the exact same, and one of them is a little bit different. And so the first method that we'll do for a trig integral is for me to know what to do, I need to pay attention to the power with sine and cosine. And so for the first method, I observed that the power that is married with sine, I found out that that's odd. And to give you all a quick reference, I'm going to use Yitz for the formula. That shows a general definition for any odd number that we can ever think of. Plug your favorite number in for k, or favorite integer for k. You'll get out an odd integer at the end. And so here, the power that is married with sine is odd. So let's review how we tackled that. If the power married with sine is odd, wasn't careful with where my hand landed on my tablet. If that is odd, then what we do is we take one sign away. So that means in my integral of sine to the m, since I know it's odd, I'm going to rewrite as 2k plus 1 times cosine raised to the nth of x equals sine raised to the 2k power. But the way I'm going to rewrite sine to the 2k power is sine squared raised to the kth power times cosine of n, and I'm going to move that extra sign I took away, and I'm going to actually pair it with the dx. Now the reason why I wrote sine to the 2k power as sine squared, all of that raised to the kth power, is because I want to rewrite this as, using my trig identity, 1 minus cosine squared of x raised to the kth power times cosine to the nth power times sine of x times dx. And now the reason why I want to substitute in sine squared to 1 minus cosine is my overall strategy will be, after that step, I want to do a u sub, where u is cosine of x. And then you'll have negative du is equal to sine of x, d of x. So that's my strategy if I have a trig integral where the power married with sine is odd. I'm going to rewrite take one sign away, put it with dx, replace sine squared with 1 minus cosine squared. Then I do a u sub, where u is cosine. I say that if we know method 1, we also know method 2. And that is if the power that is married with cosine is odd. And here's why I say I know how to do method 2 if I know method 1. Essentially, we're going to repeat method 1, but replace wherever I did a sine in method 1, I replace with cosine. So if the power with n is odd, I want to take one cosine away. I want to use a trig identity to rewrite cosine squared as 1 minus sine squared. And my u sub will be sine of that, and my du will be cosine of that dx. So method 1 and 2 are the same method. They'll be dependent on which power is odd or even. And I'll mention method 3. And this is the least common, but I think we should mention it. And that is if both the powers with cosine and sine are even numbers. Or I can rewrite an integer as 2 times the another integer. I can't do the nice trick that I've done in methods 1 or 2 in this case, because we'll mess up our u sub scenario. If this occurs, then what we need to do is to use our half angle identities. And I'll write both the identity for sine squared and also the half angle identity for cosine squared. So the main idea with a trig integral, if both sine and cosine are even, is I'm going to use my half angle identities and I'm essentially going to treat the integram as a polynomial with respect to cosine of 2x. So when you have this product, what I mean by treat as a polynomial, if I need to FOIL, I can FOIL properly. If I need to factor, I can factor as well like a polynomial. 3 is the least common of the trig integrals with sine and cosine, but just in case you do see it, I want to make sure we talked about it. All right, and with that, let's do a practice problem with a trig integral of sine and cosine. So the problem that I want y'all to try is sine raised to the cubed power cosine raised to the 6th power of x d of x. to try to integrate that using trig integrals. I'll give y'all about 5 minutes to work on it before I go over to solution. And if y'all have questions for me, please let me know. Oh, thank you, Matthew. Thank you for that catch. I can't read. There we go. Thanks for pointing that out. Alrighty, y'all. How's GizPalm going for y'all? Is it going great? It's going good. Got some comments from people for the problem. I kind of wanted to know how everyone's doing. All right. Good. That's fine, Unique. We can double check that when we go over to solution. All right, so I have 3 people who reported that they've got it pretty done. In that case, I'll give about another minute or two to let other people catch up before we go over the solution. Alrighty, let's go to the solution. So the one that has the sign or the odd power is the sign, which means I'm going to follow the same algorithm that we do when we have an odd power for sign. So let's tackle how we do that. So first, let me respond to a message. And there we go. All right, so because the sign has the odd power, I want to take one sign away to give me sine squared of x times cosine to the 6 of x. And then that one sign gets to be married with that dx at the end. Now I get to replace the sine squared with my identity 1 minus cosine squared. And I get the integral of, let's replace that with another pink, 1 minus cosine squared of x times cosine to the 6 of x, and times that sine of x dx. Now I do my u sub, where u is going to be cosine of x, and my du will be negative sine of x d of x. I have a sine of x appear in my integral. I have a d of x appear in my integral. I don't have a negative sign, which means I have to move that constant to the other side of that equation. So that means sine of x d of x will be negative du. So now that I have my u sub ready to go, I now have, after subbing, the integral of 1 minus u squared times u to the 6 times negative du. I could factor that negative sign up to the front, but what I'm going to do is I'm going to distribute that negative sign to that 1 minus u squared to give me equal to the integral of u squared minus 1 times u to the 6 times du. I'm going to distribute that u to the 6 to both of them to give me the integral of u to the 8th power and u minus u to the 6th power. And now I say that we get to win and reap the benefits of our hard work. Because now I'm taking the antiderivative, where the antiderivative is by power rule, and that is u to the 9th over 9 minus u to the 7th over 7th. Because I completed the evaluating the antiderivative portion, I now include a plus c. But because I did a u sub and I started with a function with respect to x, I sub back in what I called u at the very beginning, which was cosine. So my final answer will be cosine to the 9th power of x over 9 minus cosine to the 7th power of x over 7 plus c. Alrighty, there's our trig integral with sine and cosine to tackle. I'll give y'all a minute to finish writing that down. If y'all have a question, please go ahead and submit your question about it. Alrighty, now let's talk about a trig integral where I have tangent being multiplied with secant. And there are two main scenarios that we're going to see with it. And the main scenario is, first I'm going to deal with when I have that n. And that's going to be when secant is even. How do I deal with that? So the way I'm going to deal with that is I'm going to take away a secant squared of x away from there and marry it with the d of x. So let's look how that looks. I now have tangent and power of x, secant of x of n, which I now know is even. So it's 2 to the kth power of x, d of x. I'm taking away sine squared in it. That's going to be our main point, unique. We're going to do tangent m to the x. I'm going to take away a secant squared to marry to d of x, which means I'll have left behind a secant squared of x raised to a k minus 1 power, and that secant squared of x is married with d of x. Now I'm going to use a different identity with the secant squared I have inside that parentheses. I'm going to use another trig identity to rewrite it as tangent to the n power times secant squared of x. Our trig identity is tangent squared plus 1. And now I have a secant squared of x. d of x. And as Unique mentioned, is another u sub, where in this scenario, my u will be tangent, and I have my du for free right off the bat. So unlike before, if the power with secant is even, I want to take secant squared away from it and do the trick that we've done before. So now the next scenario that we're going to talk about is what do we do if the power that is with tangent m is odd. We're going to take away again, but this time we're taking away a secant of x, and we're taking away one tangent of x to go along with it. So what that looks like is we altered our integral to be, let's replace that with 2k plus 1 for reference for odd. When I take one tangent away, I'll have a tangent squared over k power times a secant to the n minus 1 power of x. And then I have a secant of x times a tangent of x with a d of x. Now I'm going to replace a trig identity with the tangent squared, and the trig identity that I'm going to replace is secant squared of x minus 1 to the kth power. And so in this scenario, our new u sub for this trig integral is u is secant, and d will be secant of x times tangent of x, d of x. And that's how we tackle a trig integral if we have the power with tangent to be odd. And so with that, time for the next practice problem to practice on. And I want y'all to try to evaluate the following trig integral. Tangent squared of x, secant to the 4th power of x, d of x. I'll give y'all about 5 minutes to work on it before we go over to solution. And if y'all have questions, please let me know. Alrighty. Time to go over our solution for the problem. So secant is even. So I'm going to fall under the methodology of 1, which is for the integral that I'm working with, I'm going to take away a secant squared and marry it to the d of x. So I take 2 away from that power, so secant squared, and that other secant squared is being multiplied by the d of x. Now for that secant squared that's still there, I'm going to substitute it with a trig identity. And I'm going to substitute it with the trig identity of tangent squared of x plus 1 times secant squared of x d of x. So now I'm all set for my u sub. So let's do that on the side. My u is going to be tangent in this scenario, and my du is going to be secant squared of x times d of x, which I already have in my integral, so I'm good to go. And so what I get after subbing is the integral of u squared times another u squared plus 1 times the du. Going to distribute that u squared through both of those terms, and I get u to the 4th plus u squared du, which means is now equals to u to the 5th over 5 plus u cubed over 3. Since I've done evaluated my integral, I do a plus c. And since I've done a u sub, I now write my answer back in terms of what I called u at the very beginning. So my final answer for this problem is going to be tangent to the 5th power of x over 5 plus tangent to the 3rd power over 3 plus c. And that will be my final answer for that example. Excuse me. If you have a question, feel free to type it out. As you're copying and typing it down, I want to let Catherine make an announcement.
Let's see. Can y'all hear me? Hopefully. Maybe.
I can hear you fine.
Yeah.
Okay, cool. But yeah, so this is my last class, but I just wanted to say thanks for letting me be y'all's PAL leader. Y'all are a fun group, but I missed that we couldn't be together at the end. So I'm here for whatever y'all need, even in semesters to come, if you have questions about classes, especially mechanical engineering. But tonight is our last PAL session. It's open to any questions that y'all have. And the link to get into that session is in Canvas. But y'all worked super hard. You're almost there. And I hope y'all's final goes really well. And feel free to ask questions even next week and stuff. But y'all got this. And yeah, thanks. Hope y'all have a good summer. And I'll probably wave to you if I see you next year. But all right, thank y'all.
Thanks, Catherine. Alrighty. All right. Does anyone have any questions about that example? If you do, type it in the chat. Otherwise, time for the next integration technique, which is trig sub. And always when you do think of trig sub, the way that I think of when I should use a trig sub is, does my integral contain blank? And so to summarize trig sub, I want to summarize it with a table. And so when I use a trig sub, my thought process is always, what does my integral contain? Does it contain any of these following inside the integrand? Some number squared minus another number being squared times x squared, or I alter where the b squared s squared is and the a squared is, vice versa with subtraction, or I do it with addition. So depending on what I have in my integral is going to affect what type of substitution that I do in my integral. And the way we do that is there we go, is I ask myself, what trig identity does that look like? For the first integral, or the first thing, if my integral contains the first row, the trig identity that I'm going to marry with that is the 1 minus sine squared equal to cosine squared of theta. For the second row, if I see an integral that contains b squared times x squared minus a squared, the trig identity that I want to marry with it, or looks like, is secant squared of theta minus 1 equals tangent squared of theta. And as for the third trig identity, I'm going to marry, if I see it contains a squared plus b squared times x squared, I want to marry that with the identity tangent squared of theta plus 1 equals secant squared of theta. And that's going to tell me what substitution I'm going to do based on that scenario. So for the first row, I want to do a 1 minus sine squared of theta equals cosine squared. But for the first row, I have a constant of b squared being multiplied to x, and another a squared being added to and subtracted. And so my thought process is, and when I have the constant that's not paired with the x squared, divide it by the constant that is with the x squared. And based on whatever trig function that is, that's what I have. So for the first type of integral, if I contain a squared minus another number squared times x squared, the trig sub that I'm going to do is x equals a divided by b times sine of theta. For the second integral, or if my integral contains b squared times x squared minus a squared, my same mentality is, I want to use that trig identity data looks like. And so for the second row, my trig sub will be A divided by B times secant of theta. And same thing with the third row. I want to get to use tangent squared of theta plus 1. So if I see a integral that contains a squared plus b squared times x squared, the trig sub that I'm going to do is x equals a divided by b times tangent of theta. And that's going to be my scenario to work with that. Now, another thing that I recommend if you do have a trig sub type of problem, draw a triangle out to marry with what you're doing. And the reason why I recommend that is because if it was an indefinite integral, we're doing what we do for indefinite integrals, which means I have to substitute back into with respect to x. And so the triangle that I draw is going to act like my key when I need to substitute and rewrite with respect to x. So if I have to do the following trig sub of x equals a over b times sine of x, let's write out how my triangle will look like. All right, oh, sorry about that. So that should be b over, that should be theta, not x, so sorry about that. So to multiply both sides by b over a, I have bx over a equals sine of x. In terms of a right triangle, sine is opposite over adjacent. That means if I do a trig sub with a over b times sine of theta, my opposite side will be b times x. My hypotenuse will be a. And if you use the Pythagorean theorem, you're going to get inside your square roots a squared minus b squared times x squared, or exactly what the integral contained at the very beginning, which may be forced to use trig sub. Let's do that same triangle legend scenario with the secant trig sub. So x equals a over b times secant of theta, which means b of x over a equals secant of theta. If cosine was adjacent over hypotenuse, then that means secant is going to be hypotenuse over adjacent. So for my triangle, my hypotenuse will be b times x. My adjacent side will be a. And for my opposite, I can use Pythagorean theorem to solve for, this will be b squared times x squared minus a squared inside the triangle, or what's inside the square root is what my integral contained that forced me to use trig sub. And now let's finish this up with the triangle that we need to go back in terms of x if I used tangent. So x equals a over b times tangent of theta. So bx over a equals tangent of theta. Opposite over hypotenuse. So my opposite side will be b times x. My adjacent side will be A, and my hypotenuse using Pythagorean theorem will be the a squared plus b squared times x squared, or inside the square root, what was contained in my integral that forced me to use tangent for my trig sub. And like I mentioned before, if you're doing a trig sub, especially for an indefinite integral, I highly recommend that you use the triangles as a key so you can convert back to x appropriately. And so with that, time to do a practice problem where we have to use a trig sub. So here's going to be our trig sub example problem. I want y'all to try to evaluate the following integral. 1 over x squared, square root of x squared plus 16 times d of x. I want y'all to try that one out. I'll give y'all 5 to 10 minutes to work on it. And if y'all have questions, please let me know. All right, give me a status report. How's this problem going for y'all? No, this one is probably pretty long. All right. Thank you for admitting that, Unique. And that's why we're here for practice, to make sure that we are going. Wonderful. All right. All righty. In that case, let's go ahead and tackle the solution. And like I said, the fact that trig sub is hard, I know it's hard because I think on test 2, trig sub was one of the harder topics on test 2. So let's go over that. So always my first thought, if I need to use a trig sub, is I need to check, does my integral contain one of these 3 forms? In this case, my integral does contain that. It contains an x squared plus another number. So that means I'm in the form a squared plus b squared times x squared. And in this case, the constant that is with the x squared is 1. 1 squared is 1. So that means b will be 1. And a, in this case, since I have 16, that number is a squared. And 4 squared gives me 16. So that means because I have an integral that contains a squared plus b squared times x squared, what that means is that my trig sub is going to be tangent. So x equals a over b, or 4 over 1, times tangent of theta. Because I have the integral that contains a squared plus b squared times x squared, my trig sub will involve a tangent. I take the ratio of a over b. 4 divided by 1 will just give me 4. So 4 times tangent of theta is what I'm going to define for x. Now, just like with u sub, I'm going to figure out what d of x is. And that means I'm going to have to take derivative of 4 times tangent of theta, which means I'm going to have 4, derivative of tangent is secant squared. And because my variable that I'm going to substitute in is theta, I have to do a d theta at the end too. And so here's what's going to happen with the substitution. I'm going to replace d of x with the 4 times secant squared of theta times d theta. And anywhere that I see an x in my original integral, I'm going to replace with 4 times tangent of theta. Gotcha, Nate. Yeah. And that's a good thing to point out. One common mistake is to forget to take the derivative to get dx. And so that way I can integrate with respect to theta, not with respect to x after the substitution. So, got everything good to go. So let's now take the integral of 1 over x squared times the square root of x squared plus 16 times d of x. So what I get after trig sub is the integral of 1 over, wherever I saw an x, I want to replace with 4 times tangent of theta. Since I had an x squared is substituted in there, times the square root. I see another x in here, which means I substitute in a 4 times tangent of theta in there. And because I had an x squared, that's going to be squared as well. Plus 16 times, now I'm going to replace d of x with 4 times secant squared of theta d theta. So right now, this is a very ugly and nasty mess. Let's try to clean up that ugly and nasty mess to make it a whole lot better to work with. First thing I want to do, since I'm multiplying two fractions, I'm just going to move the 4 times secant squared of theta to the numerator. Divided by 4 times tangent. All of that is being squared. So I'm going to square the 4, and I'm going to square the tangent. Which means I'll have 16 times tangent squared of theta plus, or times the square root. I'm going to square that as well. You give me 16 times tangent squared of theta plus 16 d theta. So there's what it looks like after I try to simplify that. Before I go any further, I'm going to go ahead and draw my triangle on the side, so that way when I convert back to x, I already have my legend or key over here for me. So because I had to deal with tangent, x divided by 4 equals tangent of theta. So my opposite will be x, my adjacent will be 4, and my hypotenuse will be the square root of s squared plus 16. I'm going to use that at the very end when I need to convert back into x. But now let's go back to the integral, and let's try to simplify. First thing that I'm noticing, 4, 16 outside the square root. Oop, missed 4. So that 16 in the denominator reduces down to 4, and the 4 in the numerator is gone. Next thing I notice is within my square root, I have a common factor of a 16, which means I can factor out a 16 to give me the integral of secant squared of theta times, or divided by 4 times tangent squared of theta, square root of 16 times tangent squared of theta plus 1. And a d theta over there. Now the reason why I put the tangent squared plus 1 in the light blue is now I get to use back in my table up above what trig identity does it look like? If I had an integral that contains a squared plus b squared times net squared, it looks like the identity tangent squared plus 1 equals secant squared of theta. And this is now the step that I'm going to use that fact now and replace that tangent squared plus 1 of theta plus 1 to secant squared of theta, giving me the integral of secant squared of theta divided by 4 times tangent squared of theta square root of 16 times secant squared of theta d theta. Square root of 16 is 4. Square root of secant squared will be secant. So I now have the integral of secant squared of theta over 4 times tangent squared of theta times, after evaluating the square root, 4, let's get rid of that dot, there we go, of 4 times the secant of theta. And I'll replace that with baby blue, d theta. Here I can do a little bit more simplification. I have a secant of theta in the denominator. I have a secant squared of theta in the numerator. So I'm just left with 1 secant of theta in the numerator. I have a 2 4's being multiplied together. So that's going to give me 16. Because that is a constant inside of my integral, I can take it outside of the integral. And because 16 is in the denominator, I will take outside of the integral 1 over 16. And I've left inside the integral a secant of theta times a tangent squared of theta d theta. So right now that still looks pretty ugly. Let's try to get this into a nicer form for us to work with. Here's what I'm thinking of for the nicer form. First, let's split up these two fractions just so I can have secant of theta times 1 over tangent squared of theta. And then the d theta as well. Now, my thought process to try to make this look nicer is the following. I'm going to rewrite everything that I have in terms of sine and cosine. Secant, I could go ahead and quickly rewrite that in terms of sine and cosine, because that's just 1 over cosine of theta. Tangent is rewritten as sine over cosine. The squared will mean that tangent squared is sine squared over cosine squared. And because the tangent squared is in my denominator, this whole thing in terms of sine and cosine will be cosine squared over sine squared of theta. And that's going to be my next line for this. So 1/16 times the integral of 1 over cosine of theta times cosine squared of theta divided by sine squared theta d theta. I have a cosine in the denominator. I have 2 cosine squared in the numerator. That means I have 1 cosine left in the numerator, which means I now have in my integral cosine of theta over sine squared of theta d theta. And so for here, there are 2 ways that you can take this integral. One is you could do a u sub, and I'll write that down on the side. You could do a u sub here, and for yes, my u would be sine of theta, because the derivative of sine will be cosine, and so for my u sub, I would have 1 over u squared. Another way that you can evaluate this integral, which will be the method I'll do, is rewrite the integrand in terms of another. Where it's easy. See a comment? You're close, Isaac, but it won't be negative cotangent because the derivative of cotangent is negative cosecant squared. I'll get negative cosecant at the very end because the derivative of cosecant is negative cosecant squared times tangent. Nope, you're fine. And so let's finish this up. 1/16 over, since I have 2 sines in the denominator, sine squared, I'm going to marry one of those sines with the cosine in the numerator. And then have a 1 over sine on the other side. Cosine over sine is cotangent. 1 over sine is cosecant of theta. Meaning I have 1/16 times cotangent of theta times cosecant of theta. And as mentioned in the chat, I'm going to get negative cosecant because the derivative of cosecant is negative cotangent of theta times cosecant of theta. I don't have a negative sign in my integrand, which means that I'm taking derivative of negative cosecant to give me cotangent times cosecant, which means that the integral will be negative 1 over 16 times cosecant of theta, since I already evaluated my integral, to plus c. Note that if you did method 1, where you did a u sub, where u equals sine, you will get the exact same conclusion with that integral. But I'm not done yet, because my answer is with respect to theta, and I started off with x. So now I'm going to have to go back to my triangle and convert that cosecant of theta all the way back in terms of x. So here's my legend key. And I now need to use that to evaluate cosecant. Cosecant is 1 over sine. And in terms of a right triangle, if sine represents opposite over hypotenuse, then cosecant is hypotenuse over opposite. My hypotenuse for this triangle is the square root of x squared plus 16, and my opposite is x, which means for my final answer for that integral, I'm going to now replace the cosecant back in terms of the original variable x, which we concluded to be the square root of x squared plus 16 divided by x, and include the plus c. And that will give me my final answer for that problem. Now, any questions about this problem and about how I went about to solve it? As you'll saw, took us a decent amount of work in order to get to our final conclusion. So if you need me to scroll up also to get something that I wrote down, feel free to let me know. Well, all right, so like I mentioned, any questions on this sample or any questions in general, since I notice it's almost 5:30.
I guess I have a question. Tomorrow, are we doing partial fraction decomposition?
We can, since we didn't talk about it. Okay, my main goal for tomorrow is to mainly talk about series, but since partial fraction is another part from Unit 2 that is very difficult, I feel like I'll definitely go through it. So I can spend the first part of tomorrow talking about that.
Nice. Okay, awesome. I hope you have a great day.
Thank you. You too. All right. Thank you, Jake. I knew you meant an exclamation point. That's fine. All right.
Have a great day, Scooter.
All right. See you, Anthony. Any other questions for me? Stay here for about 3 or 4 more minutes in case anyone who's still here. Helpful. Alrighty. Got a private message, so I'll respond to that. All right. Matthew, you seem to be the last one left. So do you have any questions for me? If not, we'll go ahead and end my chat. All right. Hope you all have a fantastic day, and let's stay strong. and let's get through the last week of finals.